Przepraszam, to ja tu losuję.
Okay, I think it's time to start. We are now live on YouTube and here on Zoom. So welcome everyone to our next Warsaw University Astronomical Observatory Tuesday seminar series. Today we have our first talk in a new series. We were listening recently about gravitational waves mostly, and today we switch topics to more maybe technical and scientific about space observations and science done from space, or potential future science done from space. And today we have an honor to host Andrzej Pigulski, Professor Andrzej Pigulski from University of Wroclaw Institute of Astronomy, who's going to tell us about the proposed UV observatory and photometric observatory in ultraviolet. Andrzej, please.
Good afternoon, everyone. I would like to thank Łukasz for inviting me to give this talk, and I very much regret that I can't be in Warsaw, but we have time, as we know, with the COVID, so we have to work in this way. So I'm great that I can see you, but I hope that you can see me and my presentation. So I'm going to talk about the project I'm involved in for already several years, UVSat, the photometric observatory in ultraviolet space observatory. Okay, as you can see, there are many people in Poland involved in this project, in its formulation, the scientific side and the technical and management side. There are many people, there are many more, in fact, involved than the list which I show here. But before I will present the UVSat mission, a few words about the other mission I'm also involved in, which is the BRITE mission, because this is ongoing mission. And in some sense, the UVSat mission is a successor of BRITE mission. So a few words about this mission, because about these missions are or will be in using relatively small satellites. The BRITE mission is a mission which started, in fact, the first launches were in 2013, but the mission itself started, well, more than 12 years ago. And the idea was to build a small, this is the size of 20, the cube of the size of 20 by 20 by 20 centimeters, and low mass is about 7 kilograms telescope, satellite hosting a very small telescope, 3 centimeter diameter, and then call it CCD. To observe, of course, only bright star, because with such a small telescope, we can observe only very bright stars. And so this main scientific goal of this mission was to variability study. Poland was the third country which was involved in this mission. The first two were Austria and Canada, who decided to build, each of these countries decided to build 2 satellites. And because of the idea of Sławek Grudziński, I will say a few more words about him later on. Sławek idea was to involve also Poland in this project. So this was successful, and Poland also built 2 satellites. We know them, they are named LEM and values. And these 6 satellites were launched in 2 years between 2013 and 14. 5 of them were working. So one Canadian satellite didn't detach from the launcher, so it didn't work at all. But the other 5 satellites worked and are still working very efficiently. 3 of these satellites are equipped with the red filter, the other 2 in the blue filter. So by now, we observed more than 50 fields, because the strategy of observation is to observe a given field, which is quite large. This is about 20 arc degrees. In each field, some stars are selected for observations. These are, of course, bright stars. And such a field is observed typically for 5 to 6 months, which is quite a long time. So we in general have uninterrupted runs, uninterrupted photometry for many targets, lasting 5 or 6 months. Of course, there are many fields which are reobserved. So for some fields, we have already 7 runs, 7 years, because since 2013, we have some satellites are in operation for already 7 years. So by now, we released data for over 650 stars. And we have now about 90 scientific publications. Of course, there will be more. The mission is going slowly to the end, because 2 of these 5 satellites seem not to work anymore. I mean, the Austrian BRITE doesn't observe anymore because, well, it don't react for orders from the ground, so something went wrong there. And it seems that one of the Polish satellites, the LEM satellites, also have troubles. There's still hope it will be recovered, but we don't know this. So a few words about BRITE mission, because that was a high risk, in fact, project, because there was no such small satellites used for doing science from space before BRITE. So a few words about the most important BRITE discoveries, because this shows that such a small satellite is a very good satellite. So first of all, among those 650 stars, we have many very interesting stars that lack photometry, not accurate photometry from the ground, just because everybody who did photometry from the ground knows that it's very difficult to make a precise photometry from the ground for very bright stars, simply because such bright stars practically cannot be observed with the CCD photometers. In the old times, when other detectors were used, so some comparison stars were needed, which are close. Well, bright stars, it's practically, it cannot be. It's very difficult to find a bright star which is close to the other bright star. So that's why there is no precise photometry for bright stars from the ground. Of course, there are different atmospheric effects which also spoil photometry. So the space photometry for bright star well, it's the only option to get a very precise data, of course. So using BRITE data, we found pulsations in many hot stars, about 25 beta Cephei and or hybrid beta Cephei SPB stars were found thanks to BRITE mission. And it occurred that hybridity is very common among these stars. This was not known earlier just because some modes, especially G modes in these stars, have very small amplitudes. So with the limited precisions of ground-based data, these G modes were not detected. Next discovery was on the BE stars. So again, hot stars. This practically resulted in some breakthrough in our understanding of the role of pulsations in the mass transfer. There are several papers on this issue led by Dietrich Bade, who showed that the pulsations, especially G-mode pulsation, may play a crucial role in the transferring matter from the fast-rotating stars to the decretion disk, which surrounds BE stars. The other discovery is the discovery of so-called heartbeat stars, but about massive heartbeat stars. So the first star, the massive heartbeat, was Iota Orionis, and this star also shows tidally induced oscillations, which is also an interesting thing. Next, O-type stars. We have observed about a dozen O-type and the Wolf-Rayet stars, and they also show very interesting variability, especially the variability due to stellar wind. But for some stars, we showed that there is a connection between the structures in the stellar wind and in the stellar surface, especially so-called hotspots in some stars can be present. And there's also some other type of variability which comes either from the internal gravity waves or substellar convection, which is also predicted by models in these very massive stars. Next, we found pulsations in distorted closed binary massive stars. I will show one example later on. And last but not least, we observed one of the nova, which, well, that we were very, very lucky. I mean, because we observed a star which was not very interesting, but we found that a nearby star erupted as a nova, and the nova occurred to be very interesting because it showed flares in the optical domain. And at the same time, simultaneous gamma ray observations were taken of this nova. So this allowed to show that these flares originate in shocks, and the shocks, at least in this nova, radiate a significant amount of energy of the nova, of the whole nova. So let me show this nova. This was nova Carina, a nova discovered by the SSSN project. The arrow shows the location of the nova. The nearby bright star was the star which was included in the bright list for observations. This is not very interesting K-type giant. And it occurred that close to the star we observed, something else occurred. Well, the one word of explanation, these images are defocused because that's the normal type of observations in bright mission. So another star occurred close to HD 92063. This is the nova. So the light curve from bright look of the combined light from these two stars looks like this. You can easily see the nova eruption and some flares. Two bright satellites observed, in fact, the nova. The observations were started with the Toronto red filter satellite, and the second part of the project with some overlap, Hevelius Polish bright satellite, also with red filter, continued the observations. So the observations cover more than 140 days in this case. And as you can see from this paper by Heidi et al., which was published in Nature Astronomy, there is the optical flares observed by BRITE and the gamma ray flares observed by Fermi satellite coincide quite well. So at least these three flares which was observed by the two observatories. Okay, so in general, finishing this bright part of my talk, in general, bright data reached our expectations. So we expected, in fact, that relatively good photometry would be obtained for stars brighter than 4th magnitude. Now, after all these years of observations, we know that the median magnitude of stars observed by BRITE is about 4.5. So the faintest targets are about 7th magnitude. There are some stars of 7th magnitude observed by BRITE. This is, I would say, much more than we expected. And for the best observations, for the best observed stars, the amplitudes we can detect for periodic signals reach 0.1 or 0.2 millimax. So this is quite good for a 3-centimeter telescope. So in general, the mission can be regarded as a success also because this is not the end. This is an ongoing project. We still collect data and we still publish papers from the photometry using BRITE data. But a second message, which is all very important, is that nanosatellites nanosatellites in general can be used to do a very good science. So there is an increasing interest in launching small satellites to do science. In this slide shows how many nanosatellites. Well, I should say that nanosatellites, by definition, is a satellite which is with a mass less than 10 kilograms. So nanosatellites, as you can see, there's a growing number of nanosatellites which are launched for different purposes, also for making science. So at present, about 400, 500 nanosatellites is launched or predicted to be launched each year. This is a lot. Of course, we have a problem with space debris due to these satellites. So some methods of the orbitation of these satellites also have to be predicted if such a satellite is going to be launched. Okay, going to the history of this UV, not nano, but microsatellite, because UVSat is a satellite which would have a larger mass, about 50 kilograms. So this is no longer a nanosatellite, it's so-called microsatellite. So the history of UVSat dates back to late 90s of the 20th century, when Sławek Gruczyński and Kieran Carroll, both from the University of Toronto, Canada, had a discussion or led a discussion about what would be the first Canadian scientific astronomy satellite in astronomy. So the conclusion of these discussions they made at that time was the plans to build a small, which means less than 100 kilograms satellites for science. There are three different options. The first option was to build a satellite which can do precise visual photometry in a small field of view. The small field of view means less than 1 degree. The other option was the precise, a similar satellite, but with a much larger field of view, about 25 degrees. And third option was the satellite for ultraviolet photometry, also in a large field of view. So, in fact, the first option was realized, was chosen at that time. So that's the way in which the MOST satellite, the microvariability and oscillation of stars MOST satellite, was chosen as the first Canadian scientific satellite in astronomy. It was launched in 2003 and worked till 2019. In April 2019, it was decommissioned. So it was quite a successful mission, long-lasting, 16 years is quite a large time. It's sometimes called a suitcase in space because it's the size of a suitcase. The telescope was 15 centimeters. The field of view was about one degree. But it occurred that after, when MOST was close to the end of its mission, The BRITE mission was proposed. So this was the BRITE mission is in fact the second option they chosen, because that's the small satellites with the large field of view. So BRITE satellites is the second option, and it seems that the third option also can probably be launched in the future. This is UVSat, so the ultraviolet photometry with a large field of view. Okay, that's not the end of the history. So at least this option to make a photometry from space in ultraviolet, precise photometry, occurred in the late 90s. However, at that time, it was not chosen to be built. But, well, in 2010, when BRITE satellites were still not launched, but Canadian, well, all these three countries started to build the satellites, there was a proposal. In fact, it was the discussion, there was a discussion whether one of Polish satellites, which means Heveliusz, the second Polish satellite, BRITE satellite, couldn't be made with the ultraviolet filter. In fact, the discussion on this was triggered by a young astronomer from Warsaw, Łukasz Wyrzykowski, who contacted Sławek Gruciński, asking him if it's possible. Łukasz, if I'm wrong, please correct me. But as far as I know, it was you who asked about the possibility of making one of Polish BRITE's a UV satellite.
I think it's about right, yes.
Yeah. So, well, at that time, unfortunately, it was too late to change detector, because with this detector we had in BRITE's, it wouldn't be possible. Also with the optics. So at that time, it was too late. I mean, to take this concept seriously. So Heveliusz was launched as a satellite with the red filter. But I mean, many people discussed this possibility and had it in their heads, considering the possibility. So about 5 years later, I was contacted by a group, by Sławek in general, but Sławek had a discussion with you, Łukasz, and Stefan Mochnacki and Tomek Zawistowski, if I remember all the names correctly. So, and Sławek asked me if I would be interested in defining scientific goals for such a mission. I mean, the ultraviolet photometric satellite. So in the October 2015, some preliminary scientific goals of this photometric mission were defined. And there was later in early 2016, there was a call for, I mean, I wrote several letters or many letters to Polish astronomers, asking them if they are interested in doing science with photometry with such satellites, if there is interested now. So the response was quite nice. So I could extend the list of scientific goals for these satellites, for these photometric satellites. At the same time, the spectroscopic version of the ultraviolet satellite was also considered. And there were other people who worked on the possible scientific goals of such a spectroscopic mission. Because there was a call for that, in September 2016, we prepared in a large group, which was led by Marek Sarna from Astronomical Center, a preliminary feasibility study for Polish space agents. So 11 different institutions took part in these preparations. So we prepared the document, this preliminary feasibility study when there were different versions of the UVSat, which was photometric, spectroscopic, and combined photometric and spectroscopic as well. There was no money to build a satellite at that time, so this was also only money for making a feasibility study. But this was a very important step in the development of the project, which because we had to think it over, we had to define well scientific goals, we had to think about the technical problems that can be that we have to face on. So this was a very important step in the history of UVSat. And the next step was the possibility to submit a proposal to include the UVSat project into a so-called Polish roadmap of scientific infrastructure. That was the project was submitted by Marek Sarna in July 2018, and it occurred to be successful. The decision on the inclusion of the project into the roadmap, it was January 2020, so early this year, and that was the starting point to write an application for European money to build the UVSat, and not only the UVSat, but also two ground station. This was within so-called POIG 4.2. So there was a consortium of 4 institutions built, 3 universities and the Astronomical Center in Warsaw, with the Astronomical Center as the leader of this project to prepare this application. This is not an easy money for us, because this project has to have a commercial part, which was not easy to fulfill, but we finally, all these conditions were fulfilled, so we submitted the project. And a few days ago, we got the decision that we didn't get money, unfortunately, for UVSat. However, I hope this is not the end of the story, because we have a very good project which still can be built. It is well justified scientifically, and this is technically also possible. We know that. Also because the project in the form which is now can be in fact built by many Polish companies. So this is a very important added value, not only for the scientific institutions, but also for companies in Poland which work in science industry to build such a project. Okay. So it's time to tell about the UVSat itself. So the original assumptions about the basic assumptions of the project, from this time on, I will describe only the photometric version of the project. I would like to remind that in the past there were also other versions of these satellites considered. So the photometric satellite will be devoted to the study of photometric variability of objects in ultraviolet. That's the crucial thing. But we, at the beginning at least, we thought about a single telescope, ultraviolet telescope. But later on, we decided to add another one, which can observe in visual band, just to have a 2-band possibility to observe. We know from BRITE, because BRITE is also a mission which observes in 2 passbands. However, a single satellite observes in 1 passband, but there are blue and red filter equipped satellites in BRITE constellation. So it's very important to have independent observatory who can observe in 2 passbands. Many other missions, photometric missions like Kepler, TESS, CoRoT, and other had only possibility to observe in 1 passband. So this is something very important from and new, because there are many variability variables, stars or variable objects in general that behave differently in different passbands. So especially in visual and ultraviolet gives an extra information about the possible origin of this variability. So 2 telescopes with aperture of about 10 centimeters, one observing in ultraviolet, the other for observing in visual. Of course, detectors will also be different in general. As far as field of view of both telescopes is concerned, we would like to have quite a large field of view, about 10 degrees in diameter, just to have many targets in the field. So this is important that we can observe many targets at the same time. How many? Oh, well, this is a question of the field which is observed, but a typical value which we consider for this telescope is 100 or so, of the order of 100 per field, maybe even more. The orbit is low sun synchronous for different reasons, also for the reason that the data have to be downloaded in a regular way. So this low orbit is, well, is probably the only possible orbit that we can choose. And what is very important, that observing campaigns will last from 1 to 6 months, depending on the field, with the possibility, of course, of observing multiple fields simultaneously. This is this option we have in BRITE. So some BRITEs during some campaigns observe 2 fields. So during a single orbit, 2 different fields are observed. So we can get observation for 2 different fields. Okay, so what we have, well, one important thing about UVSat is that there is a very small number of time series photometry and ultraviolet in general. So in the past we had, of course, such ultraviolet satellites like TD1, OAO2 and 3, ANS, IV, and GALAX. Some of them did time series photometry ultraviolet, but for the number of stars which have such a photometry is really very low. This is one example. This is the ANS observation from the 70s of eclipsing binary, delta Pictoris. So you can see in 6 different passbands, ultraviolet passbands, the eclipses. But what's interesting is that the star shows also pulsations. So the frequency spectra, which are shown on the right-hand side, show us a pulsation at about 6.5 cycles per day, with amplitudes, as you can see in the passband, which is at 155 nanometers. The amplitude is over 8 millimax. In the 330 nanometers, the amplitude is about 5 millimagnitudes. In visual, the amplitude is about 2 millimagnitudes. So this shows clearly that pulsations have usually a much larger amplitude in the ultraviolet than in the visual, which is very fortunate. And as I will show in a minute, these amplitudes can be used to identify pulsation modes. So at present, we also have some observatories which can observe in the ultraviolet. This is, of course, Hubble Space Telescope. This is Swift Satellite, XMM Newton, and AstroSat. These 3 space observatories can have ultraviolet telescopes. They are of the diameter, well, not all, but 2 they have diameter 30 centimeters. The other have even larger aperture, but the field of view is very small. in comparison with UVSat, so it's 17 or 28 arc minutes. So of course, these telescopes are very rarely used to do time series photometry. So they do photometry, but it is, well, very rarely time series photometry. So in comparison to UVSat, to our goals, these telescopes can be used, but they have small field of view. And because time is shared with other experiments, usually the X-ray experiments, they are rarely used to do time series photometry. This is one of examples you probably know because this is the B X-ray binary in the Small Magellanic Cloud that is building a circumstellar disk. You probably have seen this picture because all observations are compared here with the ultraviolet photometry made by UVOT telescope. This is the top panel. But in general, such a photometry, such long-term photometry, as in this case, is very uncommon. I mean, okay, so looking at the UVSat mission in comparison with other planet or ongoing missions, we can say that this satellite, this mission would fill an observational niche because there is practically no competition. No other satellites can do long-term, by long-term I mean longer than 1 month, uninterrupted photometry of a large number of stars in ultraviolet. And of course, that such a mission would be complementary to many other ground-based satellite projects aimed at the study of variability. I mean, mainly Gaia mission, for example, and other planet also mission like Plato. So some technical details of the mission, of the planet mission. So we chosen ultraviolet band, which is between 200 and 300 nanometers, just because of some technical limitations. So maybe the range between Lyman alpha line and 200 nanometers would be probably better. It is very useful for spectroscopy and ultraviolet because there are many lines there. But for photometry, because of limitations of the different types of optics, it is much easier to build a satellite which can observe in this range between 200 and 300 nanometers. So that was the range which was chosen. And the other visual band was chosen to be centered at 550 nanometers, which is a typical visual band which can be, this is more or less close to the most bands of wideband observations, space observations by other satellites. So our colleagues in the Space Research Center built a mock-up of the satellites. It was because of its this view. It was nicknamed Wally. If somebody watched the movie Wally knows what I'm talking about. Just because it has 2 eyes, these 2 telescopes. And a few words about the possible science with this ultraviolet satellites. So there is a long list of possible science that can be done, but the most important is that because we focus on ultraviolet, so the obvious targets are hot stars. Hot stars mean stars, massive stars at the main sequence or close to the main sequence, and evolved stars. I mean, white dwarfs and hot subdwarfs. Of course, white dwarfs, hot subdwarfs are quite faint, but with this telescope and long exposures, we also plan we can reach the brightest of these targets. So this is the extension with respect to the bright satellite. Bright satellite cannot observe white dwarfs, but UVSat could do that, especially because some of these stars, especially these pre-white dwarfs, are very hot, so they are quite bright in ultraviolet. So the asteroseismology, this is the technique which could be used if we have precise photometry. So we have what is needed to do successful asteroseismology is, of course, the minimum number of modes which are observed. So we need precise photometry, long-term precise photometry, and we need to identify these modes in terms of spherical harmonics. Especially the second requirement for this, to fulfill this second requirement, the ultraviolet photometry would be very, very useful, because for many modes, these are the amplitude ratio as a function of wavelength for different modes for a model of a massive star, which shows that that in general the amplitudes in ultraviolet are several times higher than in the visual, and this amplitude ratio depends strongly on the mode, on the degree of the mode. So this degree can be identified, which is very important for asteroseismology. Another type of diagram which can be used for identification is this amplitude ratio versus phase difference diagram, which also can be used to discriminate different values of L just because they separate in this diagram, especially if we have a photometry in ultraviolet. So this is the very interesting possibility, very important possibility for making good asteroseismology. But of course, not only pulsating stars can be observed with UVSat. Practically all different massive, or in this case, the most massive stars, O-type stars, Wolf-Rayet stars, luminous blue variables, the early type supergiants, and of course, very interesting group of heartbeat stars, eccentric massive binaries, can be observed and can benefit from UV photometry. This plot shows that even for such important stars like Asteroidus, which is luminous blue variable, the ultraviolet photometry is very, very scarce, and so such observations would be in ultraviolet would be very, very important for studies of such stars. Next group of stars that can benefit from ultraviolet photometry is, of course, the massive binaries. Practically all cases of binaries in which at least one hot component is present. So not, I'm listing here massive binaries, O-type binaries, which are, binarity among massive stars is very common, as shows this plot. This is much more common than among low mass stars. So all these interesting groups of binaries, high mass X-ray binaries, B X-ray systems, as we have seen in the plot I showed several slides ago, and the double periodic variables. All these groups would benefit much from ultraviolet photometry. And of course, ultraviolet photometry can also help a lot in combination with ground-based spectroscopy, of course, to derive masses and radii of massive stars, as we can see in this diagram. From the DepCap catalog, the number of determinations of masses and radii for massive stars is still quite low. So we still need precise determinations of masses and radii, especially for massive stars. And of course, these white dwarfs, subdwarfs, and pulsating pre-white dwarfs, which are, some of them are very hot, There are many groups of pulsators among these stars, so they are variable, and there's practically no UV photometry for these stars. They have short periods, so of course this is a serious limitation for also for the space photometry. But for the bright stars of these types, we can try to get interesting information on the pulsations of these stars as well. Stellar astrophysics in general, it's not the only possible science that can be done with the UVSat. So this was not considered at the beginning, but it seems that we can observe with UVSat also some extragalactic sources, especially luminous and superluminous supernovae. In particular, there's such phenomenon which is called shock breakout flare, if a very short, a few hours long flare that can be observed in ultraviolet, as shown in this in these plots. This yellow stripe shows this flare, which, as you can see, with quite a large uncertainties as measured by Galaxy satellite, but it would be very important to observe similar thing in other supernovae. Of course, supernovae, this is a very beginning of the supernova explosion. So, I mean, it would require monitoring possible sources of where supernova can erupt. This is not an easy task, but it is possible with UVSat to observe this kind of transient phenomena in general, especially if for some fields quite far from the galactic plane. So I think it would be very interesting to do this kind of observations, to observe some areas of the sky rich in bright galaxies like Virgo cluster, for example, to monitor for the possible supernova explosions, and especially for these shock breakout flares, because they can, looking at what Swift observed, at the supernova observed by Swift during the first decade of its observations, we can say that some of the brightest supernova in the sample can be easily reached by a smaller telescope, which UVSat, and can still be observed. Okay, and the next thing is also only the brightest AGNs could be probably observed with UVSat. And especially if they show some type of variability, it's very important to see if there are phase lags between ultraviolet variability and variability in the visual and in the infrared domains, because it can tell us where the variability originates, either close to the supermassive black hole or quite far from the supermassive black hole. Depending on the origin of this variability, these phase flags will be either like in this picture on the right hand, that we first see the variability in ultraviolet, then at longer wavelengths, this shows that variability occurs close to the supermassive black hole, or it depends and is the opposite. There is still a debate where the variability of this in this accretion disk occur, in which part of disk occurs the variability. So this ultraviolet observation can be crucial for solving this puzzle. This is not all, of course, because we have many other targets and many other phenomena that can be observed with UVSat. in this preliminary, and later in the feasibility study, we attach it to the last applications. There's a detailed discussion how these different stars, especially stars and not only the single stars, but binaries or multiple stars that host at least one hot component, can benefit from a UV photometry. But well, on some other phenomena, like for example, occultation by Kuiper belt object can also be observed, or even comets. Okay, so this is more or less the UVSat sky. This is the stars from the TD1 satellite down to magnitude 9.5, showing the location in the sky stars which can be easily reached by UVSat. So they are mostly located close to the galactic plane, which is the whole sky in the galactic coordinates. Of course, we have many bright stars in this gold belt, but also there are many objects quite far from the galactic plane where we can try, which are bright in the ultraviolet. So also some missions or some runs focused on stars or in general on objects which are quite far from the galactic plane can be considered. So the observing strategy is, of course, still to be defined, and once the mission will start and will have money for that. But the general plan is to cover 10 to 30 fields in 3 years of nominal operation of the satellite. And each field between 50 and 500 targets per field. This would give an enormous number of objects with a very good time series photometry in the ultraviolet. The spatial resolution will be about between 10 and 20 arcseconds per pixel. So of course, this is a moderate resolution, which depends because we want to have a large field. This is of course the price we have to pay. So very close objects cannot be resolved, especially let's say in dense open clusters on the objects like that couldn't be resolved stars in such clusters. Some details of the orbit, I have already said that this will be low sun-synchronous orbit. The possibility of observing multiple fields, I also mentioned that. Time resolution, this depends, of course, of the scale of variable, time scale of variability we expect, but the minimum time will be about 5 seconds. We also consider stacking images. This also depends on the detector, a few words on that. But what we would like to have high is the duty cycle. So minimum 60% of observing time and 20% of the all time of the satellite spent on a given orbit. This would allow to gather enough photons to reach the magnitude about 11, as you will see in the photometry, with a precision of better than 1 millimagnitude for an object per orbit. This is the aim of the photometric. This is aimed photometric precision we would like to have. Well, this also, of course, these requirements indicate for a possible detector. So the CC detectors, of course, especially in ultraviolet, are not good for this purpose. So the detector we consider it is so-called charge injection detector, which were already used in space. This is slightly different physics like CCDs. It's different physics like CCD. And the advantage these detectors have is that that the pixels can be addressed individually. So we can we can set different exposure times for different filters. This means that for bright stars, for example, the pixels covered by a bright star can be read out much more frequently than pixels that integrate photons from a faint star. Next, there is a possibility of so-called non-destructive readout, which means that the same pixel can be read out many times, and because of that, this readout results in a much smaller uncertainty of the signal measured. And these detectors are also radiation resistant, which is very important in space. We know from BRITE that the detectors degrade with time just because some pixels, there are some traps which are caused by protons. And of course, photometry degrades as well. This is not the case for this kind of detector. The disadvantage is still quite high dark current, but the newest detectors of this kind has this dark current quite low, so it's possible. Okay, of course, the some requirements for the onboard computer, for the memory and transmission rate. This is obvious that with many targets we will have need transmission about 2 gigabytes per day, which is quite high as for the requirement for such a satellite. So going to the conclusion of the talk, there are many strong points of the mission because we have an experienced technical team which has an experience from the BRITE mission. I mean, both the scientific team and the team of engineers that built BRITE satellites. In general, the space-related industry in Poland develops very fast. So we think that UVSat can be designed and built primarily in our country, excluding maybe detectors and some other parts of the satellite. So we have also experience in the calibration analysis of the data. And of course, there is a lot of scientists which are interested in doing science with this data. So the mission would really fulfill a very important observational niche. Also because such a projects like this one triggers many ground-based projects and ground-based observations. We know that we now have access to ESA telescopes and different observing networks. We have also many personal contacts that would help in this case as well. Okay, and this mission would be complementary to the other satellite missions. So the final slide, of course, we also talked about making UVSat a constellation mission. This is, of course, possible once a single satellite would be built and show that it gives a useful and precise photometry. I suppose that there would be countries that would be interested in building another one and another one. So making a constellations of such satellites would, of course, increase safety of the mission. This, as we see in BRITE, one satellite doesn't work, but the other 5 worked. So it's very important to have more than one. And of course, scientific output, in this case at least, would grow linearly with the number of satellites because the number of potentially interesting objects is really very high. This is not a limited, a very small number of targets that can be observed. Of course, that would also mean larger scientific team, which means many discussions and something which science needs very much. Thank you very much.
Okay, thank you, Andrzej, very much for this nice talk. I'll do the clapping on behalf of everyone. So I hope there will be some questions from the audience. If you want to ask a question, please use the button, the Zoom button. Yeah, there is a question from Bronek Rudak, please.
Hi, Andrzej. What was the estimated cost of this project?
So the project we submitted is about 70 million zloty. I see, because it, I mean, this project had some commercial parts. So I think that, I mean, the minimum cost, or it could be built probably slightly cheaper, but I mean, an amount of money of the order of 50 million zloty is what is needed for this kind of a mission.
Okay, any more questions here? Yes, Algita.
Hello, thank you for a nice presentation. I wanted to ask you, what about the rides and the rockets? Are you planned, how to say, are you applied somewhere to, with sort of a rocket, you will gonna shot those satellites, or you're still waiting?
Well, this kind of a satellite, which is quite small, usually is launched in a company. I mean, if there are some launches proposed, and the payload is usually several or even a dozen of 20 satellites, micro, nano satellites, which are launched together. So we didn't, well, we know that there are some opportunities, and this, of course, should be agreed well ahead of the predicted launch. So at least 2-3 years before the launch, these things has to be agreed. Well, maybe not 3 years, 1-2 years before the launch. This has to be agreed, and there are many possibilities because there are several different agencies that propose launches, because this is money. We pay for this, so they offer such possibilities. This is, of course, the Americans, the Indian, Russian, Chinese, and some other, I guess.
Thank you.
Okay, next question from Milena.
Hello, hi, thank you very much. I was just wondering, because you mentioned in the recent project that there were 2 ground-based stations that were about to be built, and I was wondering why 2 and why the BRITE ground station cannot be used.
Well, BRITE ground station can be used because this is, I mean, the requirements for the amount of data transferred to the Earth is much higher. So this has to be different passband, the X passband. The BRITE ground station works in the S passband, so this is one thing. The other thing is that, probably one ground station would be enough, but in such missions, especially for BRITE, as you know, we have a ground station in 3 countries, and it happens that there is a failure in one station, and the data cannot be downloaded by this one. So at this, if this happens, the other stations downloads the data and says. So we work together. So we have in BRITE 3 stations, and it occurred many times in the past that it was really crucial to have more than one ground station. There's also a commercial value of these 2 ground stations proposed in this project, just because such ground station, if they are not needed to work with the UVSat, they can contact other satellites, and this their time, their possibilities can be just sold for external companies.
Okay, thank you. There is a question on chat. Jakub, maybe you want to read it yourself? Okay, I will read it.
Yes, this was the spectroscopic option. There's a question from Jakub Bahiński about the spectroscopic option. Yes, it was considered, the spectroscopic option. The main difficulty of the spectroscopic ultraviolet telescope is that for spectroscopy, the satellite has to be stabilized to much better. So our requirement is RMS scatter about 10, let's say 10, 20 arc seconds. For spectroscopy, the requirement would be a fraction of a second, arc second. Why? Because otherwise you won't be able to make a good spectrum. And of course, it's very difficult to stabilize a small mass satellite with such a precision. So spectroscopic ultraviolet satellite should be much more massive. Of course, spectrograph would force to making the satellite much more massive. Of course, much more massive means and much more complicated, because spectrograph, especially in space, is not an easy instrument to build. So this would cost much more than photometric satellite. This would be much more difficult technically, which probably mean that many parts of the spectrograph and the satellite we would need help from abroad to build such a satellite. I would think that the very large advantage of this project, the Photometry project, is that it can be practically, or most of this satellite can be built in Poland by Polish companies.
Okay, thank you, Andrzej. I don't see any more questions, and I think we should stop here now. So thank you very much for your talk, for the discussion. Thank you all for joining, and see you next week on another seminar here in Warsaw. Thank you.
Thank you. Goodbye.